Someone asked me to go through and explain the multiple choice for worksheet 5.4, so I'm going to do that. So for number 1, it says when some lithium chloride is dissolved in water, the temperature of the water increases. This means, so first of all, since the temperature of the water is increasing, let me close this really quickly. Since the temperature of the water is increasing, that tells me that this reaction is going to be exothermic. And so if I'm just going to type out really quickly. So that, remember, there are 3 interactions that we're dealing with. Your solute-solute interactions have to be broken, and your solvent interactions have to be broken as well. Okay, and so these are going to be endothermic because they require energy in order to occur. All right. Meanwhile, there will be a solute-solvent interaction that occurs, okay? And that is the attraction between your solute and the solvent, so water, and in this case, the lithium ions and the chloride ions, and that is going to be exothermic. So remember, if your overall reaction is exothermic, that means that your solute-solvent interactions are stronger, while if your solute-solute and your solvent-solvent interactions are stronger, then it's going to be endothermic. So since this is exothermic, I know that my solute-solvent interactions are stronger. So if I look at all these different options, it says the strength of the intermolecular forces between the water molecules is stronger than the bond energy within the lithium chloride lattice. Well, I never compared the strength of the solute-solute and the solvent-solvent interaction, which is what this is doing. So that's not an option. B says the attraction of the lithium ions to the negative dipoles of water is weaker than the attraction of the chloride ions to the positive dipole. Okay, so basically what that's saying is the attraction for the lithium ions is going to be weaker than the attraction for the chloride ions. But we don't do that either. We simply compare the solute-solvent with the solute-solute and the solvent-solvent. So that's not an option. See, the breaking bonds between lithium and chloride is an exothermic process, meaning your solute-solute interactions, that being broken. It's not, it's endothermic. So D has to be your correct answer, so let's look at it and make sure that we agree with it. The strength of the ion dipole attraction, so ions being lithium and chloride with the dipole of water, so that is your solute-solvent interactions, is going to be stronger than that's required, than the energy that is required to break your lithium chloride, so your solute-solute, or to break the water, your solvent-solvent. Okay, so that's number 1. Number 2. Inside a calorimeter, 100 mils of hydrocyanic acid and a weak acid and 100 mils of 0.5 molar sodium hydroxide are mixed. The temperature of the mixture rises from 21.5 to 28.5. The specific heat is 4.2 and the density is identical to that of water, meaning since I'm adding 100 mils of the hydrocyanic acid and 100 mils of sodium hydroxide, the total mass is going to be 200 grams since it's 100 mils plus 100 mils. So for here, hydrocyanic acid is a weak acid, so it's going to stay together. So C and D are not options. Sodium hydroxide, however, is a strong base. So I know it's going to dissociate, so this would be the reaction that actually occurs. Okay? All right, next one. For 3, what is the approximate amount of heat that is released? So if I actually did this math out, I know it's Q equals MC delta T. So Q equals my mass, so remember it's the 100 mils plus 100 mils, so it would be 200 grams, times my specific heat, which is 4.18, times my change in temperature, which is 7. Okay? And so when I do that, I get approximately 5,880. Keep in mind, if you were not allowed to have a calculator for this, I would recommend making this 4, so it would be 2 times 4, which is 8, so 800 times 7 will be about 5,600. So this would be my answer because this is, remember, whenever you're calculating using Q equals MC delta T, remember that your Q is in joules. So I'm going to divide by 1,000 and that would give me kilojoules. As the delta T increases, what happens to the equilibrium constant and why? So if you look at this reaction, because this is, first of all, if I look, keep in mind the temperature water is increasing, which means that my reaction is exothermic, which means heat is going to be a product. So if I increase temperature, that's going to cause a shift to the left. So my equilibrium constant is going to decrease, and so my answer is C. Okay. The last one says if the experiment is repeated with 200 mils of 1 molar hydrocyanic acid and 100 mils of 0.5 molar sodium hydroxide, what will happen to the values of delta T and delta H? So really quickly, if you look at the original problem up above, it tells you start off with 100 mils of 1 molar hydrocyanic acid. So now instead I'm using 200 mils. So I'm using more HCN, but I have the same amount of sodium hydroxide. So keep in mind, this is your reaction, right? So if I started off with 100 mils of 1 molar, what that tells me is I actually am starting off with 0.1 moles, right? Because if I want to know the total number of moles, I'm going to take my volume, 0.1 liters, because I divided by 1,000, multiply that by the molarity to get my moles. So I have 0.1 moles of this, and then if I did the exact same thing here, it would be 0.1 times 0.5, so I would have 0.05 moles of sodium hydroxide. Okay? And keep in mind this is a 1-to-1-to-1 ratio. So if you look at this, if I have 0.05 of OH, that means I'm going to have 0.05 of CN minus and 0.05 of H2O that react. Okay? The reason why this is important for noting, keep in mind, since I don't have equal amounts of my reactants, I have to figure out which is my limiting reactant. So since hydroxide is going to limit the amount of product I can form, it's going to be my limiting reactant because I have 0.1 moles of HCN, so that's plenty of HCN, so that's going to be my excess reactant. So if I increase the amount of my limiting reactant, yeah, that would increase my heat and cause the temperature change to be greater. However, if you notice in the problem, what you're doing is you're increasing your amount of excess reactant. So that's not going to change anything because you're still going to only produce 0.05 moles of each of your products because you're going to run out of NaOH otherwise. So your answer here is going to be B because everything's going to stay the same since you still have the same amount of limiting reactant. If instead you had more, you ended up with more of your limiting reactant, let's say I added 200 mils of this, then yes, your delta T would increase and your delta H would increase, but that's not what's happening here. So for this question, it tells you that you have a 2-gram sample of chips and it burns in a calorimeter that has 2,000 grams of water. Okay? If I take a quarter of that amount, right? If I have a quarter of the amount of peanuts, it's able to raise the temperature the same amount, but it's able to raise that temperature for half the amount of water. So if you imagined doing this per gram, right? So this is 1,000, if this were 2,000 grams of water per 2 grams, this is 1,000 grams for 0.5 grams. So this is a quarter of the amount, but it's able to raise half the amount of water. So more heat is being released by the peanuts than by the chips, right? Because the peanuts are being able to increase the temperature the same amount. Using only a quarter of the amount, it's able to raise the temperature of half the amount of water. So it's better able to heat it up. So it's going to release, if you had equal number of grams of chips and peanuts, the peanuts would be able to, the peanuts would release more energy than the chips would. Right, 7, a student conducted an experiment in which 40 mils of hydrochloric acid were allowed to react with 40 mils of sodium hydroxide. So you have equal amounts of both of these. So you don't really have a limiting reactant here. The amount of heat released was measured to be X. In a second trial, the student reacted 40 mils of 0.1 molar HCl with 120 mils of 0.1 molar NaOH. All right. So if you notice here, yes, I'm increasing the amount of NaOH, and you might be tempted to say, hey, more heat's going to be released. But since HCl is now going to be your limiting reactant, because you're going to run out of it before you run out of NaOH, the amount of heat is going to be the same. So your answer is B. All right, I figured 8 was probably the hardest one in these. It says a student mixes 20 mils of 1 molar NaOH with 20 mils of 1 molar HCl. If the temperature rose 5 degrees Celsius, what is the delta H? Okay, so Q equals MC delta T. So I have 20 mils of NaOH, 20 mils of HCl, so a total of 40 grams since my density is 1 gram per mil. My specific heat is 4.2, and my change in temperature is 5. So the answer that you should get is 840 kilojoules. Okay? But that is not consistent with, so it should be joules. Sorry about that. Okay? Because whenever you're using Q equals MC delta T, you're going to end up in joules. Then I'm going to divide by 1,000, and so this would end up being 0.840 kilojoules. Now, notice that's not one of your answers. So you got to be careful. Look at your units here. It's asking per mole of reaction. So I need to figure out the number of kilojoules that are released per mole of one of these. It doesn't matter which one I use. So let's say I decide for NaOH. So the number of moles, so it's going to be 0.02 because that's the number of liters times 1. So I have 0.02 moles, okay? That's going to be the kilojoules per mole of NaOH. And since the reaction for NaOH would be NaOH plus HCl gives you NaCl and H2O, it's going to stay 1 to 1 to 1 to 1. So for every 1 mole of NaOH that reacts, you're going to have 1 mole of reaction. And so all you have to do is take 0.84 and divide that by 0.02, and the answer you get is 42. Now, notice it says the temperature rose by 5 degrees Celsius. So that tells me that the reaction itself is going to be exothermic. And so the delta H for the reaction itself is going to be negative 42 since the water absorbed 42 kilojoules. So the reason why this is the hardest one is just figuring out that fact that you need to divide by 0.02. Okay? When a heated sample of metal is added to 20 mils of water, the temperature rose by 5 degrees Celsius. If the same heated metal were added to 200 mils of water, okay, so if you think about it, I'm going to have the same heat because it's heated to the same amount, so the same amount of heat is going to be transferred. The mass of water starts out at 20, okay, I'm going to have the same specific heat, and I'm going to have the same change in temperature, 5, okay, or sorry, I'm going to have change in temperature of 5. For the next one, if instead of 20, I use 200, notice my specific heat's the same. Since my Q is the same, basically what this is saying is what would my change in temperature have to be if I increase this by a factor of 100? Well, since this, sorry, not by a factor of 100, by a factor of 10. So if this increased by a factor of 10, that means this would have to decrease by a factor of 10 in order to get the same heat at the end. And it says that it was the same heated metal. So you know that the heat transfer is going to be the same. So to get this to be the same, 20 times 5 is 100, so this would actually have to be 0.5. So my change in temperature is going to be 0.5. Well, my temperature of water started at 25, and so it's going to end at 25.5. Okay? And the hardest part of this is just recognizing the fact that since your heats stay the same, the only thing that can change other than your mass of water, which change, would be your change in temperature. Okay? For 10, a 100-gram sample of metal was heated to 100 degrees and then quickly transferred to an insulated container containing 100 grams of water. The temperature of the water rose to reach a final temperature of 35 degrees. Which of the following can be concluded? All right, so when I am taking a piece of metal that is extremely hot and adding it to water, they're going to end at the same temperature. Okay, but since the metal went from 100 to 35, while the water only went from 22 to 35, I know that the metal had to change temperature more. Okay. However, even though the temperature of the metal changed more, remember that the heat that the water absorbs, so the Q of your water, is going to be equal to the heat that your metal releases. It's just going to be the negative of that. Okay. So the heat is the same because whatever the water absorbs equals the heat that the metal released. The temperature change will be different, but your answer is B. One thing I did want to point out, the reason why the metal experiences more of a temperature change, if you look at Q equals MC delta T, okay, the mass, that part doesn't matter because I have equal amounts of metal and water. If you notice, even though they have the same heat, they experience the same change in heat, they experience different changes of temperature. And so if you think about it, metals have a very low specific heat. Their values tend to be like 0.5 or 0.4. And so even though metals experience the same amount of heat, since their specific heat is lower, their change in temperature is going to be greater. Okay, so let me repeat that with a real world example. If you've ever been to a pool, if it's a really hot day, which would you rather stand on? A step with water on it or like the metal grating? And the answer is the water. And the reason why is water has a very high specific heat. It's 4.18. And so even though it experiences the same amount of heat that the metal does, its temperature changes less because its specific heat is much larger than the specific heat of the metal.